Hi everyone and welcome to this lecture. As you can see, we are still discussing first order ordinary differential equation, and the kind that we are going to discuss today is called a linear equation. So this is another type of first order differential equation, and this equation, that is the linear equations, have a form of the following that I am going to write down right now. So before I write down, I want you to introduce to a notation, that is the prime notation. Let's say you are already familiar with this from your calculus courses, but let me just, for the sake of completeness, write them again. So this prime means dy by dx. There is a single prime, so y double prime will mean a second derivative, and so on. If you had y triple prime, you would have the third derivative, like this. So this is just a matter of notation. We got familiar with this notation, and let's write the general form of this equation, or so-called the standard form. Of linear equations. You will have a y prime, and here we are taking this to be a function of time t. It can be anything, but t is our independent variable. So y prime of t, you can obviously get rid of this t as well, but let's just keep it for the first few lines. And then you have some function that is dependent on the independent variable. So let me just write down small in a very small fashion that t is our independent variable, and you will have this p of t, y, and there is another function q of t. So if you write this down using the derivative, this is just dy dt, p of t, y is equals to q of t. This is the standard form of our linear equation, and first we will see how we can solve this in a general manner, then we will see an example. So solving equation 1, that is this one over here. So the first thing we are going to do is that we are going to take an unknown function. So the first step, take an unknown function. Mu of t, let's say. And this is at first an unknown function, but we'll see how we can get an formula for calculating this mu of t. And what we're going to do is that we're going to multiply this mu of t in both sides of equation 1, that is this one. So now the second step is multiply mu of t on both sides of 1, that is equation 1. So if you do that, and I'm not writing t explicitly right now, but you should understand from the context that these are actually timed the independent variable dependent functions, that is, it's a function of t. So we'll write mu of y prime plus mu p y equals to mu q. Okay, this part is done. This is pretty trivial, but now comes the non-trivial step. So this is our non-trivial step. And in this step, what we're going to do is that we're going to choose mu so that the left hand side on this equation 2, let's call it equation 2, this left hand side, this total thing, let me just box it out. This left hand side will be a derivative of the product of mu y. So let me just write it down so that you can get a clear idea what do I mean. So we want to choose a mu of t, or mu, whatever you want to write over here, such that this left hand side over here, that is left hand side of equation 2, will become equal to the derivative of the product mu y. What does this mean mathematically? So this is our left hand side, right? So first write this left hand side down. So let me just write it over here mathematically. Mu of y prime plus mu py, this will be equal to the derivative of the product. That means you take this product mu y and you take the derivative of it. So d dt of mu y, or you can just equivalently write this as mu y prime. This is the non-trivial step over here. And if I do that, since this is an equation, what I can do, I can write down this expansion, that is this one. I can expand this and then I can match both sides. So let's try to do that and see what happens. And you have mu y prime plus mu py, and this will be equal to mu prime y plus y prime mu. This is coming from the product rule. And you can see that these two guys will cancel each other out, and now you have mu prime y is equals to mu p y, right? And we are taking y to be non-zero. Obviously you can take y equals to 0, but that's a trivial solution. By trivial solution I mean if you take y equals to 0, then this equation will be satisfied trivially. So we don't want that. So that's why we can get rid of this y's. So let's get rid of this y's, because what would happen if y is 0 is that we cannot, we won't be able to divide by y on both sides. So finally, when you get rid of this y, you will have mu prime is equals to mu p. But this is just a separable equation, because if you write these things in their full glory, you will see that it will look like this. I'm just restoring the independent variable dependence. And now this is a separable equation, right? Something we saw in our previous lecture. So using that idea, you can have d mu by mu, and you'll have pt dt. And now we want to find mu, because mu was an unknown function. So now we have to find it. So now we just have to integrate on both sides to find mu. So if you integrate, there will be a ln mu, and that will be equal to, obviously there is a constant over here c1, and you will have this integration of, indefinite integration of pt dt, right? So let's just write it like this. Okay, obviously there is also a modulus sign over here, means the absolute value. And after all this is done, what you can do right now is that you can invert this relation, that is, you can take this ln from here to there, that is on the inverse ln operator, that is the exponential operation, and you will finally have mu equals to some constant c, that is obviously not equals to this c over here, and you will have this exponential, and the exponent is just the integral pt dt. And using this, we can find the solutions for the linear equation, that is equation 1 over here, and we'll see how we can do that. So we are done finding mu, and remember that our equation, that is, we wrote over here this one, that is equation 2, we said that this left hand side was equals to, that is, we wanted to have something like mu y whole prime, right? And this was equals to mu q. So now we are going to use this equality over 2 and the condition in 3, our step 3, that is the non-trivial step, to find out the solution. So let's try to do it. So we are done finding mu, and this is time for step 4. So since the left hand side of equation 1 was equals to mu y prime, we can write the whole thing as mu y prime equals to mu q. And again, I'm reminding you that this is coming from this line over here, that is mu y prime plus mu py equals to mu q. But we wanted to have this mu y prime plus mu py is equals to mu y whole prime, right? This is the thing we demanded in step 3. So using this demand and using this equation 2, you can write mu y prime is equals to mu q. And now what we want to do, we just want to integrate on both sides, because if you just write it like this, then d dt of mu y is equals to mu q. You can write it like this, right? And now the trick is to integrate on both sides. So if you do the integration with respect to this t on both sides, here you will have this mu y, and here you will have mu q dt, right? Okay, and from the fundamental theorem of calculus, you can easily guess that this will be just mu y, and here there will be an integration, and obviously this integration will remain like this. We are not, because we are not choosing anything specific for mu and q, and since you have integrated this part over here, for example, if you had integrated dx, this will be x plus c, right? Some constant. So that's why you can write it a constant like c1 like this, and this will be mu q dt. And now since we are looking for y, remember we are hunting for y of t. So we want to solve for y. So first you take this c1 up to this side, so this will be mu q dt minus c1, and you can replace this minus c1 by some plus c, because it's just a constant. For example, if you had minus 2, you could always write it as plus minus 2, and if you called it c1, you can call it c. It doesn't matter. So let me just put a plus over here and get rid of this 1, and you can see that we are almost done. You just divide by mu, 1 by mu over here, that is dividing by mu on both sides of this part, and finally you will have this mu q dt plus c. And in fact we can do even more. At this point we are done, that is, at this point we are done, and this c will come from the boundary conditions or the initial values problems that you are dealing with. But we can do more, that is, we can also write this c in terms of y t0, that is the initial condition, and mu t0. So the way to go would be just putting the limits over this integration. So let's say I want to have a solution bounded like this. Let's say t0 tf, something like this, that is starts from t0 and ends up on tf, that is t final. So this is the general solution, and obviously mu is given by this equation. So let's call this the equation number 3. This is the equation. So first what you need to do, you need to find this mu, and after you are done finding mu, you can plug this into y, and you will have your, plug this into this expression and you'll have your y. So since I have written c over here, so just so you are not confused, let me just use c prime so that you are not confused. But once you get the hang of it, there will be no confusion. So if you just put on the limits over here. So let's put on the limits. This will be, obviously I'm now taking the dependencies as well. So I'm just explicitly showing out these dependencies that I didn't show in the earlier line, but you can do that or you can leave that, it's up to you. And since we are doing it for T0 to TF, there will be T0 and there will be TF, the highest and the lowest limit, and we are just replacing T with tau. It's a dummy variable, just so that you don't get confused. Obviously you can go for T as well, but it's a dummy variable, so that shouldn't matter. And d tau, and this C will come from the initial values, that is mu of T0, y of T0, just like that. And this completes our theory discussion on on linear equations. And obviously these are first order equations. You can easily guess from the derivative structure that it has the highest derivative of order 1. If it had order 2, we would call it a second order equation. If it had order 3, that is the highest power of the, not the highest power, the highest order of the derivative. So if it had order 3, we would call it a third order equation, and so on. And in the next video we are going to see how we can use these formulas to solve an linear equation of first order. Thank you.